I think we can get started now. You guys can hear me well, right? Yes. Okay. Well, sorry for doing this class remotely as well. Too many things are happening, but I will be back in Montreal by this weekend, so we will do the next class in person. So I'll probably start with some quick administrative things, like so. So the midterm grades were released, and I think the TAs will release the solution so that you can ask for regrade if needed. And the third assignment is due this week, right? I see that the Kaggle competition is going well, but there are still some teams like who haven't participated by making submissions. I think you should do it as soon as possible. Other than that, for the final exam, I think the dates are already out. So it's December 12th from 9:30 a.m. to 12 p.m. Okay. And as I mentioned before, for the finals, you're allowed to bring one A4 sheet as a cheat sheet. Okay. So you can write in both sides, but you have to handwrite it. Like, so you cannot print an A4 sheet and bring it to the exam. Okay. And you will be returning this sheet along with your answer sheet. So if you want to make a copy of it, like, you should do it before the exam. And I have also released the last 2 years finals. If you go to the schedule, you should be able to see a folder with last 2 years midterm and final exams. Any questions? Detaching the scratch sheets in the final. No, you cannot. So detaching the scratch sheet creates issues with scanning. If you really want to detach, I recommend you bring a stapler and make sure you staple it before you give it back. Okay.
I have a question, please. If we missed the midterms, how's the weight redistributions gonna work? In this case,
If you miss the midterm, then the entire weight goes to the final.
okay. Thanks.
Any other questions? Any other questions before we begin? Yes, the final is about all the chapters. Yes. And I see that there were some concerns in Piazza about the class average being low for the midterm, and some confusions about the grading criteria, right? Like, so you are only expected to get an average of 50% in the midterm and finals combined. Okay, so it's not 50% in each exam. Okay, let's begin. So today we are going to talk about neural networks. Okay, so far, like, we have seen mostly linear models, but also some nonlinear models. Like, can someone tell me what are the nonlinear models we have seen so far in this class? You can unmute yourself and answer directly, or post it in the chat as well. So what are the different nonlinear models we have seen so far?
KNN.
KNN, yes. Anything else? So we have seen KNN. Any other nonlinear methods? QDA, yeah. Anything else? Decision trees, yes. Anything else? SVM, right? Like, so if you are especially SVM with nonlinear kernels, right? Like, so nonlinear, I'm just going to call it nonlinear SVM, but it actually means SVM with nonlinear kernels, right? So yes, I think these are good, but in general, like, you can take any, yeah, random forest, I'm going to put it with the decision trees, okay? So in general, I think we can take any linear method and add nonlinear basis functions to it, and we're going to get nonlinear model, right? Which is a neat trick that we started doing, like, even from simple linear regression, right? Like, so you take a linear regression model and you add polynomial basis functions or Gaussian basis functions. Now suddenly you get a nonlinear regression model, right? So this is something that we have seen a few times in the course, right? Like, so what we're going to do today is to discuss another class of nonlinear methods, like arguably the most popular class of machine learning methods that exist right now, which is neural networks. Okay, so to start with neural networks, like, I want to take a historical route and talk about the infamous XR problem. Okay, so what is XR problem? Like, if you have done Boolean algebra in any of your undergrad courses, then you already know what is an XR gate, right? If you have not done Boolean algebra before, it's okay. Like, you can just consider this as some data set that I'm defining right now. So the XR problem is this. Like, so given two binary variables, okay, the output is going to be one only when one of these variables is one. That's what exclusive OR means, okay? So when it is 0, 0, the output is 0. When it is 0, 1, the output is 1. When it is 1, 0, the output is 1. When it is 1, 1, the output is 0. Is that clear? So as you can see, the output is 1 only when exactly one of the two inputs is 1. It's exclusive OR. Okay? Now, there is a reason why I start this lecture with this problem, because as I mentioned before, like, I think perceptrons were invented in 1950s, right? Like, and there was a lot of hype around how perceptron could be the machine learning algorithm that could solve a lot of problems, right? Like, so now after many years, like after proper theoretical study, like, so now we know that perceptrons are just simple linear classifiers, right? Like, so they cannot even do nonlinear classification. But this idea of linear classification versus nonlinear classification is something that was not clear in 50s and 60s. Okay, so in 1969, Marvin Minsky, who is actually known for many other things as well, and Papert, okay, wrote a book on perceptrons. The book is actually called Perceptrons. Okay, it's a very famous book which basically analyzed perceptrons as rigorously as possible. Okay, and one of the main examples that the book used was this XR problem. Okay, so the book argued that perceptrons cannot solve XR problem. And XR is such a simple problem, right? Like, so if you cannot solve this problem, then you cannot solve really complex problems. Okay, so that was the basic argument. Now let's try to understand why perceptrons cannot solve the XR problem, right? So I'm going to plot the data with x1 here and x2 here, and this is how the data looks like. Okay, now looking at this data, can you tell me if perceptron can solve this problem? Can perceptron solve this classification problem between zeros and ones? Anyone?
Yes.
Yes.
No,
Why?
because it's not linearly separable.
It's not linearly separable, right? Like, so there's also no in the chat. So the answer is no here, because perceptrons can only solve linearly separable problems, right? Like, they can only draw a line. Like, so if you try drawing a line here, you could draw a line like this, which is going to have 25% error. You could draw a line like this, or you could draw a line like this, right? Like, so whatever line you try to draw, you are not going to perfectly classify this. right? So the actual classification for this particular data set is going to be something like this. So you need a ellipse, right? Like, so it separates zeros from ones, or in other words, you need some sort of non-linear decision boundary. Okay, so this notion of linearly separable problems and non-linearly separable problems was not that mature in 60s. Okay, so which is exactly what Minsky and Tappert were trying to highlight. Like, so they wanted to highlight that perceptrons can only solve a limited class of problems, which are basically linearly separable problems, right? Like, so and we need to think out of the box if you really want to solve problems that are not linearly separable, right? However, I think the machine learning community really took this book negatively, and they thought, oh, this just means that perceptrons are dead end, so we should not be working on algorithms like perceptron. Okay, which is a bad conclusion for what Minsky and Tappert were hoping for. But in some sense, they really created the first machine learning winter, like where people were not interested in working on machine learning just because they thought that, oh, you can try doing these state-of-the-art things like perceptron and they're not going to work. They're not going to solve complex problems, right? Now, there's actually a way to solve this problem, right? Like, so we have studied about nonlinear basis functions in this course, right? So one way to solve this problem is to actually construct some nonlinear basis functions that would separate the data into two parts in such a way that we can draw a line in between, right? So there's one possible nonlinear basis function construction. Okay, so I'm just going to directly write it. Like, so it's creating these two features, phi1 and phi2. The first feature is and of x1, x2 bar. The second feature is and of x1 bar, x2. Okay, now if you know Boolean algebra, then you know what these functions means. Like, if you don't know Boolean algebra, it doesn't matter. Like, so these functions basically project the data into this phi1 and phi2 space, where the two zeros basically collapse. Okay, so in the original x1 x2 phase, right, like in the original x1 x2 space, right, the data looks something like this. Now when I convert this into this phi1 and phi2 space, like I'm basically projecting the data from x1 x2 space to phi1 phi2 space. Okay, so when I project the data, right, so it so happens that the data became linearly separable in the projected space. Yeah. Is there a question?
Est-ce que tu regardes le data ou le magasin? regarde GitHub ولا ليه؟
Et puis, c'est quoi le problème qu'on doit faire?
Est-ce que regarde le GitHub اللي بعثه لك؟
Je l'ai besoin
اوكي
hier.
هذيك الفيرسيون دو باز حاولت برشا حاجات مي صراحة je suis un peu déçu.
C'est pas le meilleur résultat. Hein.
Je suis un peu déçu بصراحة. والله يسعى عملت حاجة امبارح. قلت سيء وكل استغادية مارشي وكل
Okay, can you all mute? Okay, I muted, but there are too many people who are unmuted. Okay, so can you all mute yourself, please? Unmute yourself when you're asking questions. Okay, so when I project the data from the original x1 x2 space to phi1 phi2 space, the data becomes linearly separable suddenly, right? Like, so now I can actually draw a line like this, right? And when I project this line back to the original space, okay, I'm projecting the decision boundary to the original space, and that is going to get projected to an ellipse. Is that clear? Any questions so far? So this is a simple trick, right? Like, so we have already done this before. Like, so the idea here is to come up with these two nonlinear basis functions. If you know how to come up with these nonlinear basis functions, then you can project the data into the space, and the data becomes linearly separable, and suddenly perceptrons can solve this problem. Right? Any questions so far? Okay, so what have I done here, right? Like, so let's take a look at the same thing from the graphical perspective. So with a simple perceptron, it would take x1 and x2 as input, and there will be like some weights w1 and w2. There's also bias, and I'm just ignoring the bias for now. And the perceptron is going to give you some classification based on x1 and x2. Right? So this was the original perceptron that we were trying to train x1 and x2 with, and the data was not linearly separable. So what did we do? We constructed phi1 and phi2, right? And we passed phi1 and phi2 to the perceptron, right? So this is the perceptron, and this was able to solve the problem. Now, if you think about it, what we really did is we actually took x1 and x2, okay, and we constructed phi1 and phi2 based on x1 and x2, right? So phi1 and phi2 is a function of x1 and x2, okay? So then we passed this to the perceptron with w1 and w2, and that was giving the classification, okay? So in some sense, we constructed these features, phi1 and phi2, from x1 and x2, right? So this is called feature engineering. Okay, so we engineered these features in such a way that the data becomes linearly separable. Is that clear? Now, perceptron for XOR is such a simple problem, right? Like, this is a really simple task with just two variables and like 4 examples, right? Like, so I can think a bit and somehow come up with this phi1 and phi2, like the features, and solve this problem, right? However, I cannot do this for every single task in handling. So as the problem gets harder and harder, imagine you're doing image classification, right? Like, how do you come up with hand engineered features for image classification so that the problem becomes linearly separable, right? Like, it's really hard. Like, so you need to come up with creative ways of thinking about features, and you need to add more features so that the problem becomes linearly separable. Okay. In fact, this is what people in 80s and 90s were doing. Like, so most of the research in 80s and 90s is what we now call feature engineering, where basically people are trying to come up with complex nonlinear features so that simple linear classifiers like perceptrons and logistic regression can solve the problem. Okay. Now, is this a scalable solution? Like, well, obviously not, right? Like, so what can we do? Like, what can we do to make this scalable? Any thoughts? So the idea here is to manually think about coming up with new nonlinear features and use those features plus a simple linear classifier, right? Like, so how can we do better? Any thoughts? Any thoughts? Okay, so what are we doing so far, right? We are trying to learn from data. So a simple machine learning solution for
I
this
have a small
problem.
question.
Yeah.
If I understand correctly, what the third diagram, what you're explaining is that we're gonna do like a sequence of multiple perceptron.
Okay. That's important. That's an important clarification. Okay. So far in this third diagram, there is only one perceptron. Okay. So let me see if I can do this highlighter. Okay. Yeah. So far, so this is the only perceptron we have. Okay, so x1 and x2 are just the input, right? And phi1 and phi2 are nonlinear basis functions. Like, so I created phi1 as and of x1 x2 bar, right? And phi2 as and of x1 bar x2, right? So up to this, it's just the data. So once I have this data, there's only single perceptron which is taking this data as input and making prediction. Is that clear?
Yeah, thank you.
Okay, so now a simple machine learning solution for this feature engineering is to actually learn the features themselves. Okay, so instead of us manually coming up with polynomial basis functions or Gaussian basis functions or some weird basis functions like the AND function, right? So how about we learn these nonlinear basis functions from the data directly, right? Like how about we learn whatever representation for the data is going to be more useful or more discriminative for the classification problem in hand, right? So this is exactly the idea of representation learning. Okay, so what is representation learning? This is basically the idea of learning the nonlinear basis functions directly from the data. Is that clear? So instead of using fixed nonlinear basis functions, we are going to use some projection matrices that we are learning from the data. Okay, so this is exactly the idea of neural network. Like, this is what we're going to do. So we're going to take x1 and x2, right? And instead of coming up with fixed phi1 and phi2, I'm going to learn phi1 and phi2. Okay, I'm going to learn phi1 as a function of x1, x2, phi2 as a function of x1, x2. Okay, so this is, there's going to be some projection weights here. So let's call them v11, v12, v21, v22. Okay, so then we have the weights for the classifier w1, w2, and this. Okay, by the way, this classifier could be perceptron, but it could also be logistic regression. Okay, so typically we will use logistic regression instead of perceptron here. Okay, is that clear? Okay, so this architecture is a bit different from the previous architecture, because in the previous architecture there were no weights here, right? Like, so here you don't have weights here. So this is just a fixed nonlinear function, right? Instead, what we are doing here is, like, we have some weights here. So we take x1 and x2 as input and learn some projection phi1 and phi2, right? Like, these are the parameters that we are learning. These are projection parameters, by the way. Okay, so once you have this, then you're going to use the classifier weights. Is that clear? Now, this looks like a layered architecture, right? Like, so the input to this architecture, right? We're going to call this input layer. Okay, and whatever you see in the middle is called the projection layer. Okay, and whatever you see in the end is our classifier, which is also called the output layer. So clear? Now, the projection layer, right? Like, it takes input from the input layer and does some, like, linear projection followed by some nonlinear function. Okay, so these parameters that you see here, right? So these are basically the projection parameters. Okay, and the parameters that you see here, these are the classifier parameters. Is it clear? Now, this projection layer is also called hidden layer, simply because we don't care about what is there in the projection layer. Is that clear? Just give me a second. Okay, it works. Okay, so this is also called hidden layer simply because we don't care about what is there in the projection layer, right? Like, so our end goal is always classification. So learning these projections is just to make our classifier better, right? Like whatever makes our classifier better, we are good with that. Like, so we don't really need to understand what is really going on and in phi1 and phi2. Like all we need is just to make sure that the model learns some phi1 and phi2 representations, which makes the classification simple enough. Is that clear? Now, this network structure, it kind of resembles the biological neural network, which is basically a network of neurons, right? Which is why it's called artificial neural network. Okay, or ANN. Is that clear? And each of these individual unit is called a neuron. Okay. However, I really don't like to give the biological connections here simply because a single biological neuron is way more complicated than a complex artificial neural network. Okay, so this is in no way a good approximation for biological neural network. Biological neural network is way more complicated. Like so this is a simple mathematical model which kind of looks like a neural network, and we call it artificial neural network. Okay, and there are really many names to this architecture. Like so, you can call this simply neural network. Okay, sorry. It's also called multi-layered perceptron. Okay, or MLP. So multi-layered perceptron is it's kind of a misnomer. Okay, so there are not many perceptrons here. In fact, the final classification layer here is often logistic regression. There is no perceptron here. It's called multi-layered perceptron because the idea came from like how we did this kind of layered architecture for solving the perceptrons XOR issue, right? And this is also called feed-forward neural network. It's called feed-forward neural network because the data actually feeds forward, right? Like there is input layer, then the input layer data goes to the hidden layer, and the hidden layer data goes to the final layer, right? Like so, it's called feed-forward neural network, which means there are also recurrent neural networks, like where the input doesn't just follow the feed-forward fashion. Okay, and this is also called fully connected neural networks simply because there are other architectures which are not fully connected. Okay, so here it's fully connected because phi1 is connected to both the units from the previous layer, right? Like so every unit in one layer is connected to every other unit in the previous layer. Is it clear? Any questions so far? I haven't described the mathematical model yet, right? Like so this is just a graphical representation of a neural network. So now we're going to talk about how to write this in terms of mathematical equations so that you can actually implement it, right, in practice. But are there any questions before we move to the equations?
Yeah, I
Does
just want to
learning
confirm. Oh,
Sorry, what?
I just have a quick question. So every neuron is one of the learned basis functions?
So every neuron here in the hidden layer, right, is one of the learned basis functions. So every
Okay.
neuron in the input is just the input. It's just the feature, right? So, however, how each neuron in the hidden layer is basically learned non-linear basis functions, and this neuron
Okay,
is just
thank you.
classified. Any other question?
My question was about the learning processes because
We will
isn't
talk
it
about it. We are going to talk about it in detail.
okay?
So we will talk about learning. Okay, so we are taking a step-by-step approach here. Like so, I'm talking about the intuition for a neural network. Like then we are going to talk about the equations, then we will move to learn. Okay, so now maybe let's continue. So I'm going to write the mathematical equation for this model. Okay, so let's consider some prediction problem. Okay, where the input is given by some d-dimensional vector. Okay, and the output is given by, let's say we are doing a regression problem. Okay, with k-dimensional output. Okay, so we have d-dimensional input and k-dimensional output. Okay, and let's say we are interested in learning some nonlinear basis function which is 10-dimensional. There are so we have d features to begin with. We are going to learn 10 features, and from those 10 features we are going to do the prediction of this k feature, like k-dimensional target. Is it clear? Any question?
So in this case,
Yeah.
in this case, our hidden layer have 10 features, right?
Yes, the hidden layer has 10 features.
Perfect. Thanks.
Any other questions? Okay, so now how does the MLP look like here? Right. So first we are going to learn the hidden layer. Right. But first we need to write the equation for the hidden layer. Right. So what we are going to do for the hidden layer is we are going to do a linear projection followed by some nonlinear function. Okay. So I'm going to write A of x is W1 transpose x plus B1. Okay, where this A of x is called pre-activation. Okay, it's just a terminology for now. Okay, and the phi, which is basically the hidden layer, is called h of x, which is basically g of A of x. Okay, where this g is the activation function. Is that clear? Okay, so this gives us a hidden layer, right? Like h of x. Once you have h of x, then you can do the simple classification layer. So for the classification layer, so y is going to be f of x, which is O of W2 transpose h of x plus B2. Is that clear? Now, what are all the different parameters here in this model? Anyone? What are all the different parameters here?
W and the bias.
So the weights and biases, right? Like, so there's W1, okay, there's B1, there's W2 and B2, right? Now, just as an exercise, can you think about what would be the shape of the W1 matrix? So W1 is a linear projection from input to the nonlinear basis functions, right? Like, so what would be the shape of this matrix?
1K, 1G.
No. So look at the features here. So the input is d-dimensional. The basis functions are 10-dimensional. Output is k-dimensional. Okay, there is one right answer in the chat. So it's d cross 10, right? So this is going to be a d cross 10 matrix because you're taking a d-dimensional input and you're projecting it into 10 dimensions, right? So what would be the shape of the bias 1, B1? What would be the shape of B1? 1 cross 10, as that's right. Now, what about W2? What would be the shape of W2? So W2 is a matrix from the hidden layer to the output layer. It's 10 cross K, yes. And for B2, it's going to be 1 cross K. Okay? Is it clear? So these are the 4 parameters, or parameter matrices and vectors of this model. Okay? Now, typically, the G that you see here, right, is a nonlinear activation function. Okay, so why do we need this nonlinear function? Like, what would happen if I don't use a nonlinear function for G? Anyone? So look at what MLP is doing, right? Like, it takes the data X, it first makes a linear projection A of X, then it adds some nonlinearity G, right? So then you do the classification layer. Now, what would happen if I don't use a nonlinear activation function? This has to be nonlinear. Okay, so what would happen if this is not nonlinear? Anyone? Yes, so there's an answer in the chat which is saying it would behave as 2 linear regression model, right? So what would be the sum of 2 linear regression models? It's
Just
linear
one,
regression.
just
Yeah.
one, just one regression linear model.
Yes. So if you're stacking 2 linear regression model, then it is kind of equivalent to having 1 linear regression model, right? Like, so then there is really no benefit in doing MLP. Okay. Now, if you want to see that yourself, like, so here is the idea. So if I put y is equal to W2 h of x plus B2, and let's say I'm writing h of x as simply W1x plus B1 plus B2. Okay, so there is no nonlinearity here, right? So if I don't put any nonlinearity for h of x, then what would happen is I can actually combine these matrices and vectors together in such a way that this becomes y is equal to wx plus b. Is it clear? So if I don't put some nonlinearity here, okay, a g here, okay, if I don't put a nonlinearity here, then there's no point in doing MLP. Like, it's just going to act like a simple linear regression. Is that clear? Any question so far? Okay, so it is important that we actually use some activation function. Okay, so that is non-linear. Okay, so we're going to talk about activation functions now. Okay, so what are activation functions? They are basically this function here that you see here. This is the hidden layer activation function, and O is the output layer activation function. Okay, so every layer is basically a linear projection followed by some activation function. Is it clear? Okay, so now let's do activation functions for hidden layer. Okay, the most important criteria for any activation function is it has to be differentiable. Okay, because someone asked about learning, right? Like, so if you want to learn the parameters, the usual algorithm that we go for is gradient descent, right? Like, so if you want to do gradient descent, then one of the main criteria is the entire model has to be differentiable, which means the activation function also has to be differentiable. If it is not differentiable, then you cannot do gradient descent. Is that clear? So we want an activation function that is differentiable. So we're going to start with a couple of most popular activation functions, and we will see more activation functions later as well. Okay. The first activation function we're going to see is something that we have already seen in logistic regression case. It's called sigmoid activation. Okay. The sigmoid activation Okay, it's called sigma of A, which is basically 1 by 1 plus e power minus A. Okay, the sigmoid function looks something like this. Okay, it's a really bad picture, but it looks something like this with the range of 0 to 1. Okay, and this basically takes input from minus infinity to infinity, and it squashes it to 0 to 1. Okay, so this function basically squashes the pre-activation, okay, to 0, 1. Okay, and some of the nice properties of this function, it is always bounded. So it's always positive, first of all, and it is bounded between 0 and 1, right? And it is also strictly increasing. Is that clear? Other than this, it also has nice differentiation properties. Like sigma, the differentiation of sigma is basically sigma into 1 minus sigma, right? Okay, so that is sigmoid activation function. Now, one of the main issues with sigmoid is it is always positive, right? Like, so sometimes it's good to have both positive and negative features, okay, which is when the tan h activation function is used. Okay, so the tan h activation function is defined as g of a is equal to tan h of a, which is given by e power 2a minus 1 by e power 2a plus 1. So the plus and 1 are okay. So the range of this function is actually between minus 1 to 1. So it is also going to look like sigmoid, but the range is from minus 1 to 1. So it squashes everything to something between minus 1 to 1. Is that clear? For now, we are going to stick with these two activation functions, but I will talk about more activation functions either today or in the next lecture. Okay. Now, what about output activations? So what kind of activation functions we can use for output, right? Whenever you are solving simple regression problem, then you could simply use the identity function for output activation. So the output activation O, right? You don't need to put any activation function if you're doing regression. Is it clear? Now, can someone tell me what kind of activation function I can use when I have a binary classification problem? I have a binary classification problem. So what activation function I can use for the output? Sigma, right? So there are many answers in the chat, but I see sigma. Okay, now what about multi-class classification? I have more than 2 classes. What activation? We could use softmax, right? Like, so we have already seen softmax in logistic regression case, right? Is it clear? Any questions so far? Okay, so let's go back to this picture, like the equations, right? Now, you see that there are 4 types of parameters here, right? Like W1, B1, W2, B2. Now, the activation functions themselves, right? The G and O, we could treat them as hyperparameters of this model, okay? Now, can someone tell me what are all the different hyperparameters of this MLP model? So these are parameters, right? So what are all the different hyperparameters?
The function, the activation function we use
Yes,
for the hidden
G
layer.
and O, right? Is there any other hyperparameter here? Yeah, so there is actually one good answer in the chat, like, which is the number of neurons in the hidden layer, right? Like, so this, how did I come up with this 10? Right? Like, so I just randomly put a 10 here. Like, so is it a good idea to have 10 features or 100 features or 1,000 features, right? Like, so we don't know. So basically, the number of neurons in hidden layer is also a hyperparameter. Is that clear? Any questions so far? Okay, so what have we done so far? So far, we have defined the neural network architecture in terms of equations, right? Now we need to think about how to learn these parameters. But even before that, like I want to ask this question of what kind of problems I can solve with neural networks. Okay, so because we know that with perceptrons and logistic regression, we can only solve linearly separable problems. Like, so now what kind of problems we can solve with neural networks? Okay, so maybe let's take a 10-minute break, and then we will continue our discussion.